In this section, we'll be looking at related rates. What are related rates and how can we solve scenarios involving related rates? So what is a related rates problem? A related rates problem is a problem that uses calculus to extrapolate information about one rate using known information about another connected rate, hence related, relating connected. So as an example, the rate of change of the amount of gas G in a car may be affected by the velocity, aka the derivative of a position function, at which the car is moving. Hence we have that the rate of change of gas is related to the rate of change of our position, hence we have a related rate. So keys to related rates problems. So here are some keys to use. Each variable is changing as an unknown function of time t, okay? So as a result, when differentiating equations with changing variables, we must use implicit differentiation for each specific variable. As an example, suppose the universe was expanding like a sphere, okay? We know the universe is expanding. We don't know what the shape of the universe is, but let's assume it's expanding like a balloon. So the volume of the universe then would be represented by the equation equals 4/3 pi r cubed. So if we take the derivative of this, taking the derivative of both sides, we're going to have dv over dt, the derivative v with respect to time, and then the 4/3 pi is a constant. We don't worry about that. So we take the derivative of r cubed. So applying implicit differentiation techniques, we're going to get 3r squared times the derivative of r respect to time. And 3r squared is going to have the 3's cancel out with the 3 in the denominator right here, leaving us with just 4 pi r squared times dr over dt for our derivative of in this specific scenario. So now we have an equation that relates the rate of change of the size of our universe with the rate of change of the radius of the universe using implicit differentiation. The last key is that the derivative of a variable will be positive or negative if the variable is increasing or decreasing, as we saw with applications of differential calculus in 3.7. So we'll look at sample related rate scenario. This one is fairly common, and then in class we'll look at more advanced scenarios. So a 13-foot ladder is leaning against a wall when its base starts to slide away from the wall. By the time its base is 12 feet away from the wall, the base is moving at a rate of 5 feet per second. How fast is the top of the ladder sliding down the wall? So the first step we're going to do is we're going to draw / visualize the scenario. So here's the ladder of length L, okay? As the ladder slides down, the distance x is going to increase while the height y is going to decrease. In addition, we do know initial information about the length of our ladder, 13 feet, and we know initial information about the x distance of our ladder, 12 feet. If we want to figure out what y is, the initial y value, we can apply Pythagorean's theorem, y squared equals x squared equals L squared, to get y squared plus 12 squared equals 13 squared. Solving gives us y squared equals 25, or y equals 5 feet. So this is why it's important to visualize a scenario, as it helps us to geometrically interpret what equation we may need. We might either need Pythagorean's theorem or we may need trigonometry, since it's a right triangle. So step 2, in order to help us determine whether we're going to need Pythagorean's theorem or trigonometry here, is to write down information about variables and their derivatives. So in this case, we know that the variable x is initially equal to 12 feet. We know the variable y is initially equal to 5 feet. And we know that the variable L is equal to 13 feet. Now, we know that x is changing at a rate of 5 feet per second. It's increasing at a rate of 5 feet per second. So we know that dx over dt, the rate of change of x with respect to time, is going to be 5 feet per second. Ooh, just had a little burp. Maybe you might have heard it through the video. dy over dt, the rate of change of our height, we do not know. That's what the problem is asking us to solve for. And then lastly, dl over dt, the rate of change of the ladder with respect to time, is equal to 0 since the length of our ladder is a constant. All right, so now we have to determine which equation to use. Do we go the route of Pythagorean theorem or do we go the route of trigonometry? So in general, what we're going to use here in this specific case is Pythagorean's theorem. The general rule of thumb is that if you're given an angle theta, or you're asked for an angle theta, you would use trigonometry, since trigonometry relates angles to lengths. But if you're given all three lengths, or you can solve for all three lengths of the right triangle when you're not given an angle, then you're going to be using Pythagorean's theorem. So in this case, we use x squared plus y squared equals L squared. So in step 3, we set up and differentiate an equation that relates our variables, hence why I call it related rates. Please note that if any variable is a constant, we can substitute it in now so we do not have to worry about differentiating it. So we can now substitute in 13 feet per length of the ladder, and we get x squared plus y squared equals 169. The reason being is when we take the derivative of both sides, if I just leave this as L squared, I'm going to have to take the derivative of L squared, which is a pain in the butt. But if we know L squared is a constant, then we can just replace it with a constant, and then when we take the derivative of both sides, we'll get that this is 0. The derivative of this number is 0. So that's what we do next is we take the derivative of both sides. So the derivative of x squared is going to be 2x times the change in x with respect to time, plus the derivative of y squared, which is going to be 2y times the derivative of y with respect to time, equals the derivative of 169. And 169 is just a number, so we get 0. Lastly, we plug in your knowns and we solve for unknowns. So this is a step familiar to many of you all from AP Physics. So 2x times the rate of change of x with respect to time plus 2y times the rate of change of y with respect to time equals 0. We plug in 12 feet for x. Excuse me. Did I have that right? 12 feet? Yes, I do. We plug in 5 feet per second for dx over dt. We plug in 5 feet for the initial height, and then we're solving for dy over dt. Simplifying this down, we're going to get an equation 120 plus 10 times dy over dt. I'm going to neglect the units for time being, which for any AP Physics student will give them a heart attack. So at this point, we should be very good at putting in units. And as a result of solving, we're going to get dy over dt equals negative 12. And because we need to include units, that's going to be feet per second, because dy is change in height, which is feet, and dt is change in time, which is seconds. To make sure that this makes sense right here, we can actually check the sign. We know from the original problem that our height is decreasing, so dy over dt should be a negative value, which is what we see right here. We get negative 12 feet per second. And this is the steps to solving a standard related rates problem.